Hello developers out there. So last time I put out a video, we were doing this remove duplicates problem from LeetCode, where if you have a string that has duplicate letters next to each other, you end up removing those from the string and then returning the string. And we came up with a pretty cool recursive solution. And I felt like this is a lot of code. It's kind of complicated. It's doing a lot of unnecessary stuff with the recursion. But we implemented it as a recursive solution because that was kind of the thing that immediately came to mind. And it's always fun to do recursion when you see an opportunity to, even though it's usually not the most optimized thing to do. And if you go back to that video where I described the solution and where I coded out, I said as I was working on it that there should be a way to check the last value and then the current value and then to just remove them in place. So instead of having this complicated on squared solution, you end up having an on solution. And after I recorded that, I went ahead and started thinking about it a little bit more, and I realized you could actually use a stack to do this. So if you're unfamiliar with a stack, it's a last in, first out data structure. You can look it up on Google, and you get all these images that kind of represent what a stack is. You can implement a stack using either an array with resizing. If your stack ends up going out of bounds, then you can resize your array by copying it over and creating a new array of double the size, or you can use a list data structure. And using a list data structure, you're able to add items into your stack without needing to run into the case where you need to resize your array, because the resizing operation also runs an on. So any resizing, you're adding extra runtime onto your algorithm, which you don't want to do. So with a list, it might be slightly more complicated to create. But luckily, most coding languages kind of have built-in stacks and queues that you can use. So the queue is similar to a stack, except it's first in, first out. Most stacks have the operations to push, pop, and peek. So push it is how you add data onto your stack. It will go into the last entry of the list. Pop will remove the last entry of the list and store that value into a variable for you. And then a peek will just return the last value. So if you were writing all this from scratch, to do a pop operation, you would have to traverse through your list or keep a pointer to the previous node in your list and the last node in your list, so that when you do the pop that you delete the pointers and then you set your previous node to being the last node. But then you would have to regain your previous operation, and then that ends up being another traversal through your list, which is sometimes why people use arrays, because then you can just keep indexes and then move your indexes back one, but then you have to deal with the dynamic sizing operation. And again, most coding languages have built-in operations. With Java, you can use the collections library. And with Python, you can actually just use the default list object as a stack. And I'll show you how to do that right now. I pulled up Visual Code here, and I just wrote a few simple lines. I created my stack equals a list. I appended some data into the stack that's similar to the push operation. And then you can do a peek by doing the -1 index. That will return what the latest value is, or the last inserted data piece. You can print it. It'll print it just like a normal list within Python. If you were doing this with your own pre-built kind of stack data structure, you would have to go to your head node and then traverse through your list and print out each one. Again, Python has the magical list object, so you can just simply print my stack. Then you can do myStack.pop, which all Python lists have the .pop method built in, which again, it'll take that last value, it'll assign it into a variable for you, and then it will remove that value from the list or the stack. And then just to show that that value was actually removed from the stack, I went ahead and printed my stack again. By running this code, we'll end up getting the output of kind of everything that was going on. And I went ahead and did this already. So you can see the peaked value here is 2, which was the last inserted value into the stack. The full stack representation is just 1 and 2, which is to be expected. Then when we call myStack.pop and we store that in val, we go ahead and print val, and then we just see 2 here. And then you can see that 2 was actually removed from the stack, and then we just have 1. All right, now that we understand a little bit more about stacks, we can go ahead and clean up this code a lot. We don't need the left pointer and the right pointer. We can use a for loop directly on the input string. And we can also use a return string similar to a stack using some of the built-in operations that Python gives us. So return string equals empty string. To add characters onto this, we just do return string plus equals and then a character. I'm sorry, that's kind of hard to read. And that's return string. That's not the actual return string, but I'm just doing this as an example. And then to do the pop operation, similar to what you saw in the stack, we would do something like this, where we use Python's slicing notation to take this, and then we signify that we're going to slice off the last value and then store it back into the empty string. And we're going to want to do this anytime we see that a character we're looking at is the same as the character that is on top of our return string stack, which is equal to the last string that we just put in. It'll make more sense when I actually code that. So now that we've talked about what the peek operation is just by looking at the last index, how we're going to pop values off of our return string by using the Python slicing notation, and then we can use our return string as a stack by appending characters onto it as we see them. Now that we know that, let's go ahead and write the algorithm that will remove characters as we see them in a single pass, instead of doing the complicated recursion that we did before. And we can actually do this using a for loop. I said before that I didn't think we could because there was this requirement that anytime you see duplicate characters and you remove them, and then the next character equals like the one even before that you have to remove them again. Using this string as a stack will actually allow us to do that, still doing a single pass by checking the next character that we're seeing against the top of our return string. Again, it'll make more sense when I write this. So we'll just do for char in s, and then we want to do some checking that if the current character is not in the return string, then we just go ahead and add it. But if there's no characters in our return string at all, doing return string -1, this will actually throw an out of bounds index. We don't actually want to do that. So if char equals return string, we want to do stuff. We actually want to put this in a try except too. So if this throws, we can go ahead and assume that we're looking at an empty string, and we'll just add our current character into the return string. And we can do that with the plus equals char. Now, if these are equal, then we don't want to add the character, and we actually want to remove the character from the last one. We'll go ahead and cut this, and we'll move it down into our if block. And I keep hitting the wrong buttons. All right, we'll paste that down here. Is there anything we need to do now? Okay. So if the new character is not equal to the previous character on our return string stack, we'll go ahead and add that as well. I'm almost wondering if we could just do plus equals whatever and accept and pass. But I don't think that is any shorter lines. Maybe it is. Maybe it's like one shorter. That's not a big deal. Let's go ahead and run this code and see if I'm forgetting anything silly, but I think this is actually the solution. We went from 31 lines down to 14 simply by using a peek here, using a push here, and using a pop here. So this is a lot cleaner and a lot simpler to read. And that's always something you want to strive for in code, is to making your code the most simplest to understand and the most easier to read. So when other developers are working on it, they don't have to spend a whole bunch of time wondering what some complicated recursive algorithm is doing. If you haven't seen my recursive algorithm implementation, go ahead and rewatch that. And even as I work through it and explain it, it's still probably a little hard to understand. Where again, this is much cleaner, especially if you know that we're treating this return string value as a stack, and that we can do some different like removal operations, some popping operations to be able to remove things as we see them. Let's go ahead and run this. We can see input, blah, blah, blah. And that's actually because I did something really stupid and didn't return the return string. All right, now that we have our return string defined, we'll rerun this, and I think we should be good to go. So you can see input, ABBA, CA. Basically, let's walk through this real quick. If you're in an interview, you want to understand what your algorithm does. You want to be able to explain it to the person you're talking to. So we see A goes on our return string stack. We see B goes on the return string stack. We see B again, and then we check B against the head or the peaked value of our stack, and we see B there. So B equals B, and we go ahead and we pop off the B on the stack originally, and we remove the other B. So now the next thing we see, our stack ends up being A, the next value is A, and we run into the same situation where we see A compared to A, we remove the other A, and we skip the new A. And now when we see this C, our return string is empty, we push the C, we push the A, and then we return that back. Hopefully that makes sense. I'll go ahead and submit this. Hopefully we're not running into any edge cases, and this should be a lot faster, and we're also using less memory by doing this because we're not saving call stacks onto our heap. All right, there we go. Runtime, 68 milliseconds, faster than 88% of Python solutions. Looking at this, it says our memory usage is 14.8 megabytes. I went ahead and I looked into the analytics, and I think that could just be based on when you submit things in LeetCode. Sometimes it gives different values. Some of the lower megabyte solutions were using the same stack, and they were actually using an extra stack. Maybe it's because I'm using this try except here instead of checking the array index some other way. Maybe this except is using extra memory because of other magic Python stuff. That's probably it. But anyways, I think this is still the most efficient, and our runtime being 88% I think is pretty great. And again, the code is a lot more simpler, and it would be easier to extend in the future too. And having easily extensible code, I think that's what you're really striving for in software development anyways. Now that we've simplified this and we've optimized it a little bit to being ON instead of ON squared, I hope this all makes a little more sense so that when you get to your next interview or even just doing these kind of problems for your own exercise, you will understand the situation if you run into it in the future, to try to work backwards from your recursive algorithms and then coming up with something that runs in a linear time. If you learned anything from this video, please do like and subscribe for the YouTube algorithm. It'll help out the channel a lot. It'll allow me to do more of these and help out future new devs. So, all right, take care. Bye.